Okay, let's go ahead and pop this into a spreadsheet and see what we get. I'll start off by putting these guys into the spreadsheet. Delta T is equal to 0.01. So I'll put a 0.01 and call that is delta T. Yeah, let's just go with dt. And then I had G in there, 9.80. I call that A sub G. And then let's go down here and start our N column. We had a T sub N, X sub N, V sub N, A sub N, and then a V sub N plus 1/2, and an A sub N plus 1/2. Okay, this I said is set that 0. This is just equal to the one before it plus 1, and make sure that works right. Yeah. And then this I said was equal to the N times delta T, which I want to use absolute addressing, so I put $A, $1, so that it doesn't keep on shifting down to a different one each time. And then X sub N at time 0. I call that 0. So we're starting from 0 and working our way down. Downward is the positive direction. And then V sub N was given as 7.77 meters per second. A sub N, it's equal to this. No, equal to 9.8. So I'll go $A, $2, that's this number up here, and then minus, and it was 0.0225 times V squared. Now I want to check to make sure that that's what I put. V, it would be this one, V sub N, so I'll just click on that spot, and then squared. Actually, I want to check, see if I get that in part 1. Yeah, I got the squared there. Cool. So I've just typed this in. And now I need V0 plus A0 times delta T over 2. That's equal to this one plus A0 times the delta T is $A, $1. Slash 2. I wanted half of that. And that is, let's see, D7 plus E7 times delta T over 2. Okay, that looks good. Then I think in here, I'm essentially copying this one. Let's see if it works out for me. Control V. And I want $A, $2, that's the A sub G, that's cool, and then minus 0.0225 times F7, yep, I wanted this one right here, and that's what I got squared. Okay, that's consistent with what I had in here. Then I hit return on that, and on this, the T just copies down. The X is going to be, let's say it's equal to the one before it plus the velocity at the half, that's this one, times delta T, which is the $A, $1. Okay, that looks good. And then the velocity at the next time, when n is equal to 1, so at 0.01 seconds, if I'm keeping that at 100th of a second, it's equal to the previous velocity plus the acceleration that's valid for that time interval from 0 to 1, which would be the one at the half there, times delta t, in other words, $A, $1. Then the A, I can just copy that one down. We'll check, but it should be the acceleration is this, and that looks good, $A, $2, and then minus the 0.025 d8, which is this one right here, squared. So that looks good. And then the velocity at n plus a half, okay, this is going to be a little bit new. It'll be equal to this velocity plus the acceleration that's good for that time interval that goes from a half to 1.5 in this case, so it would be the one that's good at 1 times the full delta t. And then the acceleration is just calculated based on that velocity. So the 9.8 minus the 0.0225 times f8, this is what I want to check on, squared. Okay, that looks good. And I think at this stage, we just have to copy them all down. Once we get all these, it's just a copy from then on. So let's actually copy everything down. And it looks like I got problems. So this seems to have taken a big jump here. From here to here is a big jump. From here to here is a big jump. Something looks like it went wrong. So I think it was the velocity at n plus a half would be speed at n minus a half, which would be this one. So f8, it actually looks okay, plus the acceleration, e9, times, I actually wanted $A, $1 there. I think that's what went wrong. So we need dollars in there. $A, $1. I was going to A2 the next time, and I needed it to stay right there, so let's try just copying this thing down. Now it's making a little bit more sense. I've got this, looks like that 100th might be an okay step size. I'm getting up to 15 here. I think, let's actually try that many steps and see if that's going to turn out to be smooth enough. And then we might want to try doubling that later on to see if it actually works. But I think what I'll do is copy this. This is C131. So equals C131, and this is X final. And so I'll make bigger time steps. Let's try 0.03 to try to get this up to 35, so that was too big. 2. So we're about there right now. If I make it a little bit smaller, then it'll get right there. Let's see what these. Let's take a look at the graphs, see what's going on here, see if this is relatively smooth, see if it looks like it's working. So I'm going to select the X column. I'll do XY scatter, just connect them together by lines. I go x versus time. So time here, x there. I think we're done. Delete that so I can see a little bit more of it. Alright, it says this thing is starts out at 0, gets up a little bit past 35, which is where I need it. Takes about 2.5 seconds to get there. I think it makes sense. It's speeding up because we got it curved up, so the velocity starts out, we get some positive slope here, but it gets steeper and steeper. So the velocity is increasing, and that makes sense. It's got some acceleration. The acceleration is getting smaller as time goes by. It's not a constant acceleration problem, but I think that makes sense. So I'm going to copy that and then change it to v versus t and change. I'm going to right click on the data here and go source data, series, the y values, the velocities are in the d column instead of c, so I'll change these c's to d's, and let's see what we got going on here. Yeah, we showed the velocity, the speed increasing, so we're getting higher up on the graph, but the rate at which it is increasing is slowing down, so the slope of this curve is decreasing, meaning the acceleration is decreasing, which makes sense, based on the formula that we were given in the problem. The acceleration, the bigger v gets, the smaller the acceleration gets. So the acceleration is decreasing. And in fact, let's make sure that's the way our acceleration looks. I'll copy that one. Control C, Control V. Change the title first. And then quickly change the data series. The next one over from D is E, and that's where acceleration was. Next one over. I want to check and make sure. So the velocity was D, acceleration E. Okay. And sure enough, the acceleration is decreasing here. It's not even decreasing at a constant rate, but definitely decreasing. So things are making sense. It looks pretty smooth there too. I think I'll play with my time step to get that to be 35. And then look at the velocity, the very last velocity. That's in slot D131 equals D131. So that's V final. And I want to get it when this is 35, so I'll make smaller time steps. Let's try 0.0195. And too many decimals there. 0.0195. Get a little smaller. Let's chop that off. Okay, now we got to get a little bit bigger. So let's try a 3 there. A little bit. That's a little bit too big because I'm gunning for 35 right here. So try a 2. 1. Oops. 1. Now we're a little bit low. 0.15. Try 1.7. Yeah, and that to 3 sig figs is 35. So we're getting 18.917. I think I want to put that on here. So from the spreadsheet, V sub s is, I'll call it 18.92. meters per second. And then I want to try, let's say, I'll use a bunch more steps here to see if it's still going to work. So I did 124. I go 148, 248. Let's double that. Okay, one more than that. And then on here, I'm going to have to change the range of these. Now, I don't think I'm worried so much about the graphs. I want to see what this number does. If I change to look at the bottommost number, which is now 255 for both of these. So I'll go 255, 255. So it's getting much further with this time step, of course. So let's double the time step. I wonder if that'll actually work if I just exactly double it. So I'm going to copy it over here, Control C, and then edit, paste special, paste as values. So this is my old time step size, and I'm going to go over here and just say equals F1/2. Yeah, sure enough, that takes me right to 35, and I'm still getting, so I double the time step, and I'm getting the same values. So I'm pretty confident that we got a good value for the V sub f.